Okay, I guess it's 1 p.m. We'll
I
start
think
or wait a little longer.
by my
I
clock,
still have 1 minute left here.
I still have 1 minute left here too. I think you're a little fast.
Ooh, wait, okay.
And of course, Piet would know. He's at PTB, so
Exactly. There's no way I can make an argument here. So.
Yeah. So should Christian know. He's also at the source here.
Okay, now I think it's on the hour. I think people will keep coming in, but you can also probably go ahead and get started.
All right. Yeah. Well, good afternoon, good evening, wherever you are. Welcome to today's. Okay. Yeah. Let me address it. Okay. Yeah. Welcome to today's VAMOS seminar. We have the great pleasure to welcome Piet Schmidt from PTB and University of Hannover. Let me quickly introduce him. He is a professor at Hannover. He is the director of the Quest Institute there. He started physics, like his physics education in Constance, University of Constance in Germany, as an undergrad student. Then I think spent a year or something at Portland State University, came back to Constance, worked with Jürgen Wieneck on his diploma thesis, and eventually also started his PhD in Constance with a project that eventually moved with Tilman Pfau to the University of Stuttgart. Back then he was exploring the scattering properties of chromium atoms. Well, after his PhD, he got a Theodor Linden Fellowship, moved to NIST, worked with Dave Wineland, James Bergquist, did pioneering work with optical ion clocks, quantum logic, aluminum clock, and then came back to Europe, started as an assistant in Rainer Platz Group in Innsbruck, received the prestigious START Prize, set up his own independent research group, and eventually came to Hannover and PTB to develop a atomic physics research program covering aspects of precision spectroscopy, quantum logic, and in particular now, what he's also going to talk about today, highly charged ions. So yeah, welcome, Piet. Please go ahead. An optical atomic clock based on a highly charged ion. One more thing I want to mention for the audience, type questions in the Zoom Q&A. And also you can use the YouTube chat for any question. The speaker will pause 1 or 2 times during the talk, and then we'll go through those questions. The stage is yours, Piet.
Thank you very much, Christian, for the very kind introduction, and to the whole committee, a big thank you for inviting me here to speak. I look back when I gave my first VAMOS seminar, and that I think was 2.5 years ago or so. Yeah. So I'm very excited to give you an update of what has happened in the meantime. So as Christian already pointed out, I'm here at PTB. I'm currently sitting here in this building on the beautiful campus of PTB. You may know that PTB is the National Metrology Institute of Germany and the sister institution of NIST. And just as NIST, we do a lot of fundamental research, basic research, as we do in my group. In my group, everything revolves around the quantum logic spectroscopy technique that I've implemented together with colleagues for the first time during my postdoc in Dave Wineland and Jim Bergquist's group at NIST, as Christian already mentioned. And in the meantime, this has now become the center of my own group's research activities. So we do quantum engineering. We build optical clocks using quantum logic spectroscopy based on aluminum ions, for example. We study the spectra of complex ions. We control molecular ions, and I'm going to talk today about our highly charged ion work. And all of that we do to access previously inaccessible systems, and build clocks and perform spectroscopy at the highest level for applications in relativistic geodesy, measure heights, test fundamental physics of in various areas. Okay, now let me start by very simple considerations. Let me start by explaining to you the principle of microwave atomic clocks. So if you want to build a microwave clock, of course you need a microwave oscillator, and typically you choose a device that produces 9.2 gigahertz microwave frequency, and if you count that, you can display the time if you count the cycles. However, the microwave source drifts, and so what you do is you probe transition in, for example, cesium, and steer the resonance frequency of your microwave drive onto the atomic resonance frequency here by providing feedback onto the microwave source. And that pretty much implements a microwave optical clock. That's a closed loop system, and if you count the cycles, you get the time. And the first cesium atomic clocks have been developed in the 50s at NPL in the UK. And that has worked so well from the start that now since 1967, the SI second is defined based on an atomic transition, hyperfine transition in atomic cesium in the ground state. Now, of course, most of you are probably aware that we didn't stop there. We want to improve clocks further. And before that, I want to give you an analogy on how the microwave clock actually works. And it works pretty much like tuning a musical instrument. So if you have your violin, for example, and you want to tune it, you measure the frequency of the strings with a reference that tells you if the string is vibrating too fast or too slow, and then you can provide feedback and change the string tension. And then, of course, you can apply it for applications. Now, in our case, the oscillator here can be a radio frequency or a laser, and the reference is then an entire lab, essentially, where you have an atomic reference that you tune your local oscillator onto. Okay, now once you have your clock, you want to know how good it actually is, and I want to introduce the main notions. There are two main notions for characterization the quality of clocks. They're called stability and accuracy, but I would prefer the terms statistical uncertainty for the instability, and that tells you essentially how large the scatter of your data is. If you measure the frequency or the time intervals, then the scatter, the larger the scatter, the larger the statistical uncertainty. The second notion is inaccuracy, and I'd like to call that rather systematic uncertainty, because it tells you how well the measured frequency, after applying all corrections to it, actually represents the unperturbed transition frequency. And you can also visualize this as in a dart target scheme, where the scatter, where you hit the target here, can be large. It's the statistical uncertainty, and whether you're hitting the center tells you something about the systematic uncertainty. Now, of course, if you want to build clocks, we can have either a small statistical uncertainty, but a large systematic uncertainty, or we can have a large statistical uncertainty and a small systematic uncertainty. And what we really want is both to be small. So small scatter and represent the unperturbed reference transition accurately. Now, one problem with that last point here is that we don't actually have ways to calculate the reference transitions. Optical clocks these days produce 18 digits. You can't calculate that. And so we do not really know what shifts our resonance frequencies that we actually measure. And so we have to compile what we call an error budget, in which we evaluate all possible frequency shifting effects, apply a correction, and since we only know them so well, now the remaining uncertainty of applying that these corrections here is then the systematic uncertainty of the clock. And I'll give you a few examples of this later on. Now, with these preliminaries, we can now argue why we actually want to move away from microwave clocks and go to optical clocks. Now, one obvious reason is that the faster the cycles are, the better you can count the cycles and the better the statistical uncertainty. Also, what we want is very narrow transitions, very narrow optical transitions, because it's also very clear if the transition is narrow, you can determine the center frequency with much less data points. And so combining these two, the relevant quantity really is the line width divided by the transition frequency. Now, if you optimize this ratio here, then you optimize your statistical uncertainty, which is essentially the measurement time that you need to reach a certain statistical uncertainty. The second notion, however, the systematic uncertainty, can also be improved using optical clocks. We want to have very small frequency shifts of our reference transition in our measurements, and that's of course species dependent. And I will show you that highly charged ions have a huge advantage here, or have an advantage here. And since the frequency shifts here are not entirely universal, but the order of magnitude is sort of universal to all atoms, their fractional relevance becomes smaller the higher the transition frequency. For example, such frequencies can be introduced by collisions between the atoms, by moving atoms. We can have Doppler shifts if they're not cold enough, or we can have electric and magnetic fields that shift the clock transitions. But in the end, if you go to large transition frequencies, both the statistical and the systematic uncertainty can be much smaller than, for example, for microwave clocks. And therefore, the principle of optical clocks is almost identical, except we've replaced a few components. We have now a laser oscillator instead of a counter. We first have to divide the frequency down using an optical frequency comb, and then we can count it electronically again. And then the principle is the same. We probe our atoms. We usually do that using electron shelving. So if we're in the ground state and we apply the yellow laser here, then we scatter millions of photons per second. The atom appears bright, whereas if you're after the spectroscopy in the excited state, the atom goes dark when we apply that laser. And so again, we can steer our laser frequency onto the center frequency and have then built an optical clock. Okay, now let me give you a brief historic review of optical clock estimated uncertainties. Here in blue, you can see the cesium microwave clocks that go down to a level of about 10 to the minus 16 relative uncertainty. And you can see immediately that the optical clock development progresses significantly faster. And they've now outperformed cesium by about 2 orders of magnitude. And here's some of the sort of more prominent optical clocks in the world. Currently, the most accurate clock is the aluminum clock at NIST, now I think the 3rd generation or so. And then, of course, there's many lattice clocks at NIST, at PTB, in Japan, group, and many other places around the world. Now, one interesting feature is now that in this area below the blue cesium line, we can no longer give the transition frequency of these systems with 17 or 18 digits in the unit hertz, simply because the SI second is still defined on the transition in cesium and can only be realized to a level of 10 to the minus 16. That means means that if you want to give these excellent measurements, because we can't give them in hertz. Okay. Now, 18 digits, that's a mind-bogglingly small number. And the question there is, who in the world beats clocks this accurate? Yeah? And there are, of course, many applications. Foremost, we can use them to test fundamental physics. We can search for dark matter. We can look for changes in fundamental constants, test Einstein's theory of relativity, or even look for gravitational waves. There's also applications in navigation, of course, GPS or Galileo or other systems are based on good optical clocks on board of the satellites. Then we can use clocks to synchronize large networks, for example, very large baseline interferometry networks. And we can use clocks for height measurements because, according to Einstein, clocks on the floor ticks lower by 10 to the minus 16 per meter height difference on Earth than clocks that are on a table, for example. And we can use that. We can use that to compare distant clocks over a fiber, for example, and then determine the distance between the two clocks in one go. And that's a very attractive application in geodesy for Earth monitoring, post-glacial uplift, and so forth. So this is a really relevant application. And so what my talk is about, or what I would like to convey, is that in particular, highly charged ions are excellent candidates to actually perform these tests of fundamental physics. In my talk, I will give you a brief introduction into highly charged ions and why they're really good to test fundamental physics. I want to show you the state of the art in generation and spectroscopy of highly charged ions. I will then show you very briefly the experiment that we've set up together with José Crespo's group at the MPIK in Heidelberg to actually produce, slow down, and cool highly charged ions in a cloud of beryllium ions, laser-cooled beryllium ions, and then do quantum logic spectroscopy on them. I will show you the first results, and then I will also show you the systematic shifts and the clock operation of the argon 13 plus clock that we have built. I will then show you the results of the isotope shift and summarize by looking into the future. Okay, now, if you haven't worked with highly charged ions and are just used to neutral atoms and singly charged ions, then your knowledge of energy scale starts to fail when looking into highly charged ions. That is because there's a strong charge state dependence on the typical energy scale. So if we go, for example, from the hydrogen atom to uranium like hydrogen, no, hydrogen like uranium, that's uranium 91 plus, then the binding energy of the last electron goes from 10 eV to 140 kilo electron volts. The hyperfine splitting becomes gets into the visible regime, electron volts splitting now. QED effects are even more strongly enhanced. There are now hundreds of electron volts and very prominent in the spectrum. While at the same time, for example, Stark shifts are strongly suppressed by Z to the 6, as can be visualized here by the very small radius of the electron cloud of the last electron orbiting around the highly charged nucleus here. Now, to give you a more concrete example, let me show you here boron, where we have fine structure in the ground state. That's hundreds of gigahertz splitting here, whereas the first excited dipole allowed transition, or the first excited state on the dipole allowed transition is at 250 nanometers. Now, argon 13 plus has exactly the same electronic structure as boron. Here, the fine structure splitting is enhanced to 441 nanometers, whereas the first dipole allowed transition is at 19 nanometers, where it's very difficult, of course, to operate a laser. So in summary, highly charged ions are a strongly relativistic system with very large QED effects, and we can find optical transitions that we love for optical spectroscopy and optical clocks in fine structure transitions, in hyperfine structure, and in so-called level crossing transitions. Okay, what are the applications of highly charged ions? Highly charged ions have been studied for decades or almost centuries by now. And this is because they're abundant in the universe and can be used to probe cosmic and stellar processes. Here, for example, is a picture of the temperature and the magnetic field around our sun. For the same reason, they're used as diagnostic tools for plasma physics, where you can get the electron temperature of your plasma by probing the different charge states of, for example, tungsten in the plasma. And what many of you are maybe not aware of, but the latest generation of cell phones here and computers is only possible thanks to highly charged ions, because in the latest wafer stepper machines, tin12 plus produces light at 13.5 nanometers in these wafer stepper machines that produce the small structures that we need to scale semiconductor industry chips. But of course, this is not why we're interested. We're interested in highly charged ions because they offer a very simple electronic structure. So they're calculable systems. This is because they have only very few electrons left. And that they lend themselves to test fundamental physics, because we have strong QED effects, and by comparing these accurate calculations to experimental measurements, for example, of the G factor in the ground state, you can test QED in strong fields. That's a very active field. Since they're strongly relativistic and have a high ionization potential, highly charged ions have the highest sensitivity of all atomic species to a change in the fine structure constant, and therefore also the highest sensitivity to a dark matter interaction. And that means that if sort of an optical clock based on a highly charged ion, or one of these highly charged ions that has this high sensitivity, then it would appear to us as if the fine structure changes, because the levels in the highly charged ion will change. And if we compare that to other optical clocks that have lower sensitivity, then we can derive bounds for the existence of dark matter, for example, as our spaceship Earth flies through the universe and probes for dark matter. Since they're also strongly relativistic, we can use them to probe violation of local Lorentz invariance. And since the electrons are very close to the nucleus, we can probe for fifth forces using isotope shift spectroscopy. This is something I'll touch upon at the end of my presentation in looking into the future, but also parity violation. And we can, of course, do nuclear physics by performing spectroscopy on the electrons that probe very close, or that are very close to the nucleus. And there's many more applications, of course. Okay, now the question is, can we actually do highly charged ions offer all features required for optical clocks? And what features would we like to see? First and foremost, of course, we would like to have low sensitivity to resonance shifts to build an optical clock. And these are, for example, sensitivities to electric and magnetic fields. And in fact, highly charged ions have an advantage here, because many of the common shifts are strongly suppressed in highly charged ions. For example, the second order Stark shift is strongly suppressed, and the second order Zeeman shift is strongly suppressed, and the electric quadrupole shift is also suppressed in highly charged ions. Now, all other clock species requirements can also be fulfilled. So they're narrow laser accessible transitions, optical transitions. They have simple level structure to prepare the initial state. Just the detection and cooling is a problem that will then be solved by quantum logic spectroscopy. And there's actually dozens of proposals with, I don't know, tens of different species that have been proposed. as optical clock candidates. Okay, just to give you a more concrete example that this promise has actually been fulfilled now. As an example, in our Argon 13 plus clock that we've now evaluated, just for our very typical experimental conditions, here you can see the systematic shifts, the character of the systematic shift, the typical parameters, and then the shift order of magnitude. And without going into all the details, what you can see here that the magnitude of the shift for most of the shifts is below 10 to the minus 19, except for the quadrupole shift that we can get rid of fairly easily, actually, by averaging Zeeman components properly. So in fact, highly charged ions have fulfilled that promise of showing very small systematic shifts, and that greatly loosens the constraints, of course, on characterization of the perturbing fields like blackbody radiation or magnetic field perturbations or light-induced shifts, for example, and allows us then to build high accuracy clocks based on highly charged ions. Okay, with that, I suggest that we take the first break for questions, if there are any.
Yeah, thank you very much, Piet. In fact, we do have a few, so let me go through them. Oh, before I do that, however, I want to point out one thing. You don't mention it on your CV in your webpage, but you actually also very recently in 2021 got the an ERC advanced grant. So that's a really prestigious thing that I didn't want to let sweep under the rug.
Well, thank you. Yeah, that would not have been necessary to point out. Yeah,
it is. So let's go to the questions. Well, let's basically sort them according to how you structured your talk. First question, so you can't calculate these expected frequencies, clock transition frequencies. Can you learn something interesting or important from what you measure?
I think the question refers to clocks in general.
That's right.
And yes, these are the applications that I've mentioned. So we can compare clocks of different character. And for example, they can have a different sensitivity to a change in the fine structure constant. And if the fine structure constant would change because of cosmic evolution, for example, then we would see that in clock comparisons, either as a drift or as an oscillation, depending on whether alpha just drifts or whether there's an oscillation. And for the same reasons, we would also detect dark matter. Because if there's a non-zero, non-gravitational coupling between dark matter and normal matter, then that would look like that. Then the dark matter field would shift also the electronic levels in all our atoms or molecules, and that would look to us as if the fine structure constant has changed. And with that analogy, a high sensitivity to a change in the fine structure constant gives you also a high sensitivity to probe for dark matter candidates. And then, of course, another more down-to-earth application is the frequency ratio measurement between optical clocks to measure heights.
And then, well, let me go on. Yeah, I guess it's also still related to this. Also, some people are wondering, is it still useful to have these absolute frequencies? Of course, they can then just be measured with cesium precision. Can they inform more sophisticated theory calculations of atomic structure? But in addition, let me just combine this with a second sort of bunch of questions, which is sort of going in the direction of asking how trustworthy are these uncertainty budgets? Is there a way to actually verify these budgets are correct?
Okay, so let me start with the calculations. So atomic structure theory can calculate transition energies at the percent level currently. That's 10 to the minus 2 or so. Or was it 10 to the minus 4? Yeah, so we're missing a large, many orders of magnitude here. So there's no way that these spectra can be calculated accurately enough. Now, concerning the error budgets, here, of course, it's slightly different, because in sort of what we have to do to come up with an error budget, we have to come up with ideas what could actually change the levels, for example, interaction with magnetic or electric fields, and then we can calculate the shift that we estimate from measured magnetic fields and then measured atomic properties. And the atomic properties that we need to know to subtract sort of this offset, we do not need to know with 18 digits, but maybe with 3 or 4 or 5, yeah, depending on how large the actual shift is. The larger the shift in hertz, yeah, the more accurate we need to be able to calculate and measure it to be able to subtract it down to a level of 10 to the minus 18 or 19, for example. I hope that was clear. Yeah. If not, please ask again.
Let's do maybe 2 or 3 more questions. We have quite a few. So the first one, Merat Zareh is asking, what about the stability in highly charged ions? Like a highly charged ion clock, is it going to be more stable?
Yeah, you will see that in the next few slides. Very likely not, yeah, because we still have just one atom that we can probe that limits our signal-to-noise ratio, of course. And then, as at least the clock people know, and for the others, I'm just mentioning this, to get the lowest statistical uncertainty, we want to probe the clock transition for as long as possible. And then we have 2 limitations. Yeah, one is laser coherence time that might limit the maximum probe time, and the second is excited state lifetime of your atom. And in like neutral atom or singly charged atom clocks, you can have excited state lifetime spanning from tens of seconds to years. For example, the ytterbium octopole is years. So there's essentially no limit on the atom side for the probe time, but there's a limitation, of course, in the laser coherence time, and there are activities around the world, in particular also here at PTB, with Uwe Ster and in a collaboration with Jun Ye's group at GILA, to build ever better cavities to get the laser coherence time up, to exactly do that probe for longer times and reduce the statistical uncertainty. And our argon-13 plus clock will be limited by the excited state lifetime in our case, because that's just 10 milliseconds.
All right. And then Tanya Zelevinsky is asking why one should expect that AC Stark shifts due to near resonant probe light are suppressed for highly charged ions. Is it because the density of all the states is low?
Yeah, exactly. So highly charged ions have a very sparse energy spectrum or sparse level structure, because everything is stretched so far apart. The next dipole allowed transition, for example, in argon-13 plus, is at 19 nanometers, and so AC Stark shifts coupling your typical optical clock laser to that transition are essentially negligible. That's the reason.
All right. So last 2 questions. I'll bundle them again. Okay. One question is there an advantage to go to a configuration with 2 valence electrons, like many neutral optical clocks or aluminum ion clocks have? Is that an advantage or disadvantage to implement 2 valence electrons in highly charged ions? And more generally, does it make sense, or are there stable, highly charged negative ions?
Okay. Okay. I'm a bit confused about highly charged negative ions. How? So you add electrons and then they become negatively charged? Is that the idea?
Yeah, I guess the question is, can you actually do this? Can you have stable ions beyond -1 or -2?
Not to my knowledge. Yeah. I think the binding energy of the negatively charged ions is already extremely weak, and then adding just another electron might work in special cases, but they're never going to be highly negatively charged. And you would also not have the advantage, because most of the advantages that we have here come through the fact that the remaining electrons are much closer compactified around the nucleus, are more tightly bound. And you would have the opposite effect if you add negative, if you add more electrons. They become loosely bound. That might be interesting for other reasons, but probably not for the clock business. What was the first part?
First part was like many clocks, optical clocks have a 2 valence electron configuration.
Okay. I don't know, if that is an advantage or not. Currently, I haven't looked into the proposed species under this criteria yet. Maybe if somebody from the theory is online here, Mariana Savanov or Julian, or maybe they can answer this question better. I don't know if there's an advantage to using 2 valence electrons. We're currently limited by other effects, namely that if you have a very narrow clock transition and just have calculations, then it would take years to actually find the transition using reasonable laser powers. And so we need to identify species where we can find the clock transition, for example, using Rich-Rydberg combinations by going in a circle, where the clock transition essentially is one leg, and we can measure all the other legs in E-beam spectroscopy to narrow down the frequency of the clock transition.
All right, thank you, Pete. I suggest let's continue with your talk, and then we'll have another chance for questions.
Yeah. Okay. Then another advantage of highly charged ions is that there are really many of them. So this is your typical periodic table where neutral atoms live in the front row. The singly charged ions live in the second row here. And then the highly charged ions are all the rest. And as you can see from this animation, there's just a lot of them, with potentially very interesting properties that we haven't even looked at yet. And so there's a lot of room here to do interesting physics once we get, when we start looking into highly charged ions. I'm cutting the animation short here. So highly charged ions have, of course, been investigated for decades already, and typically they're investigated in a plasma in so-called electron beam ion traps, where they're produced, where we accelerate electrons to a few kilo electron volts, and then inject argon, for example, and then the electrons ionize the argon. And if you tune the parameters properly, then you mostly get argon 13 plus that fluoresces here in the green through electron excitation. You can then image the fluorescence using onto a grating spectrometer and get spectra like this, where here's the wavelength in nanometers, and you get lines that are 45 gigahertz wide and can be resolved because there's good signal to noise ratio down to 150 megahertz level. And the reason why the line bits are so large is because the effective temperature in these electron beam ion traps is actually electron volts, which corresponds to megakelvin temperatures. And so there we have huge Doppler broadening. So the problem is that the electron beams are noisy and hot. You have electron beams, you have permanent magnets, and so forth. This is not a good environment for high precision experiments. And the second problem that we're having is that there's no cycling transition typically for highly charged ions to do our cooling and efficient state detection using electron channeling. And we can, of course, solve both problems. And just to compare how singly charged ion clocks look like, we store ions in radio frequency Paul traps, where we apply a radio frequency onto these radial electrodes for radial confinement, and then we put a DC potential to these end cap electrodes to provide axial confinement, and then we trap the ions at megahertz trapping frequencies so that we can get recoil-free absorption. We can have long interrogation times. The ions here live for hours or days or even months in some cases. They're trapped in the zero field, and therefore there's only small trap-induced shifts on the ions. We can isolate them from the environment. They're in an ultra-high vacuum system. We can apply laser cooling to reduce the temperature, and then, except for the cooler interaction and the occasional collision, there's no interaction. So we can get very high accuracy. And as an example, the most accurate clock in the world is the NIST aluminum clock currently. Okay, now the idea is to get highly charged ions into Paul traps, obviously, because it's a much better environment. Now, how do we solve the second problem, the cooling and detection? That we do using quantum logic spectroscopy. Here we have our highly charged clock ion, for example, and we trap that together with a beryllium logic ion. And this is a strongly coupled system because of the Coulomb repulsion between the two ions. And we can then implement a small quantum algorithm to transfer the internal state information after probing the highly charged ion using the common motion of the two ions here onto the beryllium logic ion, where we can then use our arsenal of quantum optics techniques and detect the internal state very efficiently. So in a way, these two ions form a composite system that combines the advantages of both species. And of course, highly charged ions are not the only application. I've already mentioned the aluminum clock that works using quantum logic spectroscopy. And we and others have started to look into molecular ion detection preparation. And recently, this group also performed spectroscopy on this. Okay, now we set up such a system in our labs at PTB in a really excellent collaboration with Jose Crespo's group at the MPIK in Heidelberg. We set up a cryogenic system because we need cryogenic vacuum. Every background gas collision with a highly charged ion leads to catastrophic charge transfer, and therefore we need a very good vacuum. And we do that by having a closed cycle cryostat here, a pulse tube that removes energy from the 4K region here. And then we have mechanical decoupling here on the way to provide a vibration-free environment for our ion trap. The highly charged ions are produced using a compact electron beam ion trap based on permanent magnets. It's about 30 centimeters long. And we have then a focused electron beam impinging on the argon ions here, producing argon-13 plus and other charge states that are then being ejected from the EBIT. They fly through ion optics here, are bent around the corner. Then we have here a time of flight selector to just choose argon-13 plus. And then the highly charged ions are slowed down and then enter the cryogenic Paul trap that we have here. It's based on alumina that is gold coated and then laser structured. It's a rather microscopic trap. And the highly charged ions are injected from one of the sides here. In that Paul trap, we have pre-prepared a cloud of laser-cooled beryllium ions, and when the highly charged ion enters, then oscillates back and forth. It loses energy through interaction with the beryllium ions, and then eventually it crystallizes. And we observed the highly charged ion just as a dark spot here in the beryllium cloud. And then we remove the excess beryllium ions until we are left with a 2-ion crystal, highly charged ion, plus 1 single beryllium ion. Okay, and how does that system look like? Here's an abstract representation, simplified, of course. We have a 2-level atom with 2 metastable states, so that the transition line width is much smaller than the harmonic oscillator frequency of the joint motion of both ions in the trap. And that's a coupled system that we can fan out. resonant just with the electronic transitions and just change the electronic transition. And if we now detune our laser to the blue by exactly 1 quantum of motion here, or by the oscillation frequency of the ions in the trap, then we can change from spin down to spin up and put in a quantum of motion. Whereas if we red detune by the harmonic oscillator frequency, we can drive red sidebands that remove 1 quantum of motion in the trap. And of course, that plus reinitialization results in ground state cooling. Now we can drive these transitions, and here's an axial motional spectrum on beryllium with a 2-ion crystal, actually, where we have argon-13 plus and beryllium. You can see here the so-called out-of-phase mode and the in-phase mode that have different frequencies that we can calculate based on the single beryllium ion frequencies. And now, if you compare different charge states where the frequencies of different charge states would come to lie, we can easily distinguish argon-13 plus from the neighboring charge states in the motion spectrum. We can then apply axial ground state cooling by applying this red sideband, reinitializing, and then the cycle stops once we reach this ground state because there's no excitation possible any longer. And from the excitation spectrum here, it's obvious, the red sideband excitations need to vanish if you're in the ground state, and from the statistical uncertainty of the measurements here, we derive a mean occupation of well below 1 here in this case. So we are very close to the ground state. Now we can implement our quantum logic state transfer. We have both ions in the motional ground state of the joint motion. We then apply the spectroscopy laser that produces a superposition of ground and excited state in the argon ion. Typically one would detect now, using the electron shelving technique, but since we don't have such a transition in argon, we apply a red sideband that implements a swap operation between electronic and motional states, because it maps the excited electronic state into an excited motional state here, and leaves the ground state, the motional ground state population untouched here. We can then sort of visualize this as a joint motion of the ion crystal. It's a shared motion, so we have the same motional excitation on the beryllium, can apply the same trick there again, using a red sideband, and then map the motional superposition back into an electronic superposition, and then detect on the beryllium ion. So we have done that with the argon-13 plus and beryllium detuned across the resonance frequency, and observed the transition here. We also did Rabi flopping on the excited on resonance here, and what you can see here is a dephasing of the Rabi flops that's strictly dictated by the excited state lifetime of about 10 milliseconds in argon. Okay, that's my second break, in case there are questions so far.
Yeah, indeed, there are. Well, I guess, yeah, so the first one you kind of have already answered. It's asking how easy is it to generate a specific charge state? Yeah.
So, of course, you need to have good diagnostics, and we use as our first primary diagnostic time of flight spectra. And then you can tune the 2 parameters that you have, or the 3, the density of the atoms, then the energy of your electron beam, and then the breeding time. So it's a pulsed experiment. So we breed for about 100 or a few hundred milliseconds, actually, and then eject the highly charged ions. And depending on those 3 parameters, you can sort of single out typically 3 charge states that then are dominant, and we can use the 2 of them with very high efficiency using the time of flight, and then shuttering an electron.
Yeah, another question. Given all the advantages of the large charge in terms of systematics, is there also a downside to it? Let's say, like for instance, enhanced sensitivity to micromotion?
Yes, there is, and I'll come to that in the next slide.
Okay. And then next question, yeah, what makes an ion a good logic ion, or is there even a reason to have two logic ions with one ion combined?
That's a very good question that will also be answered together with the first one. I can teaser it already. It's all about cooling, and we pick the logic ion to have a similar charge to mass ratio as our highly charged ion, because then the cooling works most efficiently. That's the criterion we have for the logic ion species.
Yes. Then we got one question about the mini EBIT. So what kind of flux do you actually get from it for a specific charged ion, like charge state? How often does one come along?
That's a very good question. We have never quantified it actually, because it worked on the first try, and then we just moved on doing quantum logic. It sufficient, yeah. There are enough of them, yeah. That's all I can say. Yeah.
And maybe the last question for now would be, so you showed this movie with the huge number of highly charged ions. Why did you actually settle on argon 13 plus?
Yeah, that's a very good question, and that's also the reason why we're having now a harder time finding new ion species, because argon 13 plus was the most well-studied highly charged ion prior to our experiments, with an uncertainty of 150 megahertz in the transition energy through laser spectroscopy in EBIT and a recent measurement in penning traps in Sven Sturm's group. And so that narrowed down the search space for us in finding the clock transition. That was the main motivation.
All right, thank you, Piet. Why don't you continue, and then we'll have a final session for questions later.
Okay. All right, now to the challenges. And what's the downside, the possible downside of highly charged ions? As I already mentioned, there can be a large Q/N mismatch between the ions, and that means that we get a that the ions essentially almost decouple, but only in the radial direction, not in the axial direction, and that can lead to inefficient cooling of some of the radial modes. Let me illustrate this. Yeah, so if you have this large charge to mass mismatch, then the radial modes decouple in one mode where the beryllium ion moves a lot, and that of course is very efficiently cooled. And then the other mode is where the highly charged ion moves a lot, and that is very inefficiently cooled. And just how inefficiently, of course, we measured by cooling to the motional ground state here, and then heating back up to the Doppler cooling limit by just applying laser cooling on the beryllium. And you can see that it takes hundreds of milliseconds to reach equilibrium, and that's just unacceptable for optical clock operation. You can't wait for half a second, just to do your laser cooling. And so that's the downside. But on the other hand, we need the highly charged ions to be cold to not get any second order Doppler shifts or time dilation shifts. And so we've come up with a scheme that we dubbed algorithmic cooling, that's derived from techniques in NMR actually, where we again have our level diagram. We have beryllium and the highly charged ion that are both excited radially, and we can then apply a red sideband on the highly charged ion, where we remove one quantum of motion, put it into a spin excitation, and then apply again a red sideband, but this time on the axial sideband, and therefore we've transferred one quantum of motion from the radial to the axial motional mode. And the axial motional mode we can cool very efficiently just using the beryllium, and therefore perform axial ground state cooling, and then just repeat the cycle, and therefore reach the ground state. And that's a fairly generic scheme that you can use also for other schemes, large molecules or even nanoparticles, in our opinion. Here's an example how this works. This is after Doppler cooling the weakly coupled modes. And after applying this algorithmic cooling cycle, we see a strong suppression of the red sideband corresponding to near ground state occupation in bar of 0.4 and 0.2, corresponding to 200 microkelvins or less than 200 microkelvins in all modes. And this is probably the coldest highly charged ion of all time. And the beauty about the system is that it actually heats up very slowly as well. That means that with our background heating rate that we have in our ion trap of about 10 quanta per second, if we apply one of these red sideband algorithmic cooling pulses per optical clock cycle, the system remains in the ground state. And that enables optical clocks based on highly charged ions, at least concerning the motional shift, is then that motional shift is suppressed to 10 below 10 to the minus 18. Now, coming to clock operation. Of course, Argon 13 plus is not a 2-level system, but rather a 6-level system. The Zeeman levels are split by an externally applied magnetic field, and we probe 4 of these 6 transitions. Why do we do that? First of all, to eliminate the linear Zeeman shift. At the same time, it also serves to eliminate the quadrupole shift, and turning it around, we can also measure the quadrupole moment of the excited state here, the electric quadrupole moment, and knowing the G factor of the ground state, we can measure or extract the G factor of the excited state. We then probe from 2 different directions, just to not be fooled about correlated motional shifts of the ion when we apply our probe laser. And all of this is pseudo-randomized such that the drifts are suppressed, and we have interleaf measurements on the micromotion and secular temperature during the clock cycle. Okay, so here's the result of our error budget, where we have characterized and measured all frequency shifting effects that we could come up with. And of course, we don't know. I remember now there was a question, how do you verify these error budgets? You verify by comparing with another clock, obviously, because you never know whether you missed a major systematic shift. Yeah? So we have to compare to other clocks, and then if the frequency ratio does not drift, then there's at least an indication that there's no uncontrolled systematic shift in your system. But you can never be sure. Now, the first thing to notice, if you look at this error budget that I'm not going to go through in detail with you, is that it's very short. And the second one is that the shift, so the correction that we have to apply for the majority of the shifts is either 0 or very small at the level of 10 to the minus 18. There's one exception, which is the micromotion shift. That is significant in our case and has therefore also a significant uncertainty. It limits us to 2.2 times 10 to the minus 17. However, I should mention that this is not a fundamental limitation. It's a flaw, a technical flaw of our ion trap that we could not mitigate. And a singly charged ion clock would have exactly the same systematic uncertainty. So this is not a function of the charge state of the ion. By simply replacing the trap that we have with a better one, we should be able to reduce that shift significantly. And the same holds true for the AC Zeeman shift, the second largest component. This is coupling of the clock laser to that has no pure polarization to other Zeeman levels, and then resulting in the shift of the clock transition. But that can also be taken care of to a very high accuracy. So these are no fundamental limitations. So in summary, we've demonstrated here a highly charged ion clock with a systematic uncertainty at 2.2 times 10 to the minus 17. Okay, now I've mentioned that we need to verify that at least through a series of measurements that there's no fluctuating shift. And we have done that through a frequency chain comparison, so to speak. Yeah, we have here our highly charged ion clock with our argon 13 plus clock laser. We then have a frequency comb that is locked to the silicon cavity operated by Eric Benkler and designed by Uwe Sterr and Junier and co-workers. And then through a second frequency comb that is locked to the same cavity, we reference our argon-13 plus frequency to the ytterbium octopole transition frequency that is operated in Niels Hundemann's lab. And if you do the comparison, we see that we average down at 3 times 10 to the minus 14 per square root of tau. Tau is the measurement time. That's not a particularly good value, and it's limited by the excited state lifetime of the argon ion of 10 milliseconds. We can't probe for long. So we averaged down to a statistical uncertainty of 10 to the minus 16 for 2 isotopes, actually, argon-40 and argon-36. And since the ytterbium octopole transition is a secondary representation of the SI second and is known to 1.3 times 10 to the minus 16 fractional uncertainty, we now also, the argon-13 plus optical frequency is now one of the best measured optical frequencies, actually. Now, where does that put our measurement? Here's the historic evolution of frequency measurements of that transition, where we improved over the most recent measurement by 8 orders of magnitude. Also, the isotope shift has been measured before experimentally here in an in-EBIT measurement. And there's more measurements, and there's also, of course, theory calculations of this isotope shift, which can be calculated more accurately than the transition energy can be calculated. And what you can see here is our measurement. This means this work. Amplified here, this is Hertz, and before it was megahertz here. And so we have a 9 orders of magnitude improved uncertainty in the isotope shift measurement. And noteworthy is that it's one of the first experimental verifications of the so-called QED nuclear recoil effect, because if we neglect QED in the isotope shift, then we are clearly, the theory value clearly deviates from our experiment, whereas we get excellent agreement if we have the full theory, including QED. Okay, let me summarize here. I hope that I could show you that precision spectroscopy of highly charged ion addresses fundamental physics question. We have now achieved full quantum optical control over highly charged ions using the quantum logic spectroscopy technique. We've demonstrated the first coherent spectroscopy, and we've operated the first highly charged ion clock with a fairly low systematic uncertainty. We've improved previous measurements by orders of magnitude and could already contribute to tests of fundamental physics by a verification of the QED nuclear recoil. And the beauty of this entire technique and the setup is that the quantum logic technique is a universal spectroscopy scheme. So we can just replace argon-13 plus by another highly charged ion, have a new clock laser, and the main infrastructure of our experiment, which is surrounded around the beryllium ion, remains the same. And since I am a bit over time here, I want to cut this short. You can ask questions if you're interested. Let me just jump to the full conclusion here. What we want to do in the future is we have already started now performing isotope shifts in calcium-14 plus. First measurements of the isotope 40 have already been accomplished, and we will use we will measure the remaining isotopes here and combine that with data on single charged calcium ions. And with that, we can constrain the existence of fifth forces that mediate an interaction between nucleons and electrons with a 10 to the 3 higher sensitivity compared to other systems. However, for that, we need to get nuclear masses more accurately of these systems, because they go in the type of analysis that is being done here. Now, one of the next clock candidates could be nickel-12 plus, for example, that has the advantage of having a much longer excited state lifetime of 19 seconds. So the statistical uncertainty would no longer be limited. However, finding that transition with the current search scheme would take a year, considering the accuracy of the calculations that we have. And that's a year of 24/7 operation. And so we're looking into new schemes in being more efficient in actually searching for this transition. And then the next candidates are, of course, so-called level crossing transitions in highly charged ions that exhibit this strong sensitivity to a change in the fine structure constants. And there's a number of potential candidates that, however, have a similar problem that we need more accuracy or more accurate frequency data. And I should mention that there's other groups now around the world building up experiments similar to ours in Fort Collins, at Birmingham, Wuhan, and at Tokyo as well. And with that, I'm at the end of my presentation. I would like to thank my fantastic team here, now 2 generations already of people who have been working on the project, and in particular, our really fantastic collaboration with Jose Crespo and his group, without which we could not have done these types of experiments. And with that, I would like to thank you for your attention.
Thank you very much, Piet. I think we got a few more questions. Yeah, so Alessandro Banducci is asking, how long does an algorithmic cooling sequence take?
A few tens of milliseconds. So it's not a major limitation. The most time we actually spend with ground state cooling the axial mode in the beryllium.
And well, Dima Butka is congratulating you to this amazing work and is asking if you can say a bit more about yeah, if you can say a bit more about the nonlinear isotope shifts.
Oh, thanks, Dima. Yeah, so I can show the skipped slides. Okay. Okay, let me briefly start here, explaining the isotope shifts to you. So if you go from one isotope to the next, you add a neutron or more than one neutron, and then the shift in the transition frequency that you get arises from the overlap of the electrons with the change in the nuclear charge radius to first order, and the so-called recoil shift, because the mass is now different. And what we don't know very well is the delta R squared, because that comes from nuclear physics. We can't calculate it, and so we want to get rid of it, and we do that by measuring 2 transitions on the same isotopes, and then we can eliminate this delta R squared term because it's the same for the 2 transitions. And if we do that, then we get rescaled equation, and we get a linear dependence essentially on the isotope difference here. Now, if we now had an additional force mediating an interaction between the nucleus and the electrons, we could assume that it has a mass n phi. It's a scalar field, and then leads to an interaction x, the field is then described by xi. We have a coupling constant alpha, non-new physics, for example, to the normal matter. That would introduce a nonlinearity in the King's plot. Yeah? So we have this relation plus this additional term from the 5th force, and that would then lead to a deviation from the linearity. Now, what do you need to be very sensitive to these types of effects? You need transitions of very different character. And a very promising approach in this regard is to combine calcium plus isotope shift spectroscopy with calcium 14 or 15 plus spectroscopy. And here's the sensitivity, the isotope shift. So the calculated or assumed new physics shift contribution to the isotope shift. You can see that calcium plus is very sensitive to this, yeah, and by comparing it to calcium 15 or 14 plus, yeah, you get a very large sensitivity because there's a large differential shift. And using that, we can put that into these types of exclusion plots, where you have here the range of mass of the mediator particle, and then here everything above the lines here is excluded. Here's actual data. The latest data is from Michael Graveson's group, I believe. And there's hypothetical data from different species, and we would be 3 orders of magnitude better than calcium, and 2 orders of magnitude better than other species here, or more sensitive. Yeah? And then potentially can reach that wide regime or region that is not excluded yet. Now, of course, that's there are problems because there are higher order effects that also contribute to a nonlinearity in this king plot. You could call them spurions, and they lead. So yeah, they result in nonlinearity. That is not a new field that you need to subtract essentially. Yeah? And what you can do is play the same trick again that you've done with a nuclear charge radius. Just add more isotope pairs and more transitions, and if you fulfill this equation, you can remove S+1 spurions, or S spurions if you fulfill this equation. And there's a lot of experimental work on these isotope shifts, also on the theory side, of course. And here's a table that I stole from, or borrowed from, Julian Berengut, that compares, for example, the status in calcium with terbium, where a lot of data, experimental data, is available now. And you can see here on the spurions, the magnitude of the shifts of the spurions is rather small in calcium compared to terbium, and the number that will be relevant, for example, for 10 millihertz is also strongly reduced. And therefore, we are very optimistic that using highly charged calcium ions, we can actually make a difference here. Sorry, that was just a long explanation.
Yeah, that was indeed. Thank you very much, Piet. Maybe, we have a bunch of more questions, but it's running late. So maybe the final question, which is sort of an outlook type thing, I guess. Yeah, someone is asking, and I guess to some extent you covered it when you went through nickel and the other ions you suggested, but do you have a dream highly charged ion that you would really love to do spectroscopy on?
So I know all the properties that this dream highly charged ion should have, yeah, but I just don't have a name yet, yeah. So we need to keep looking, yeah. So we want a long excited state lifetime. We want an optical transition. We want no hyperfine structure because that just complicates state preparation, and we need to know the transition frequency experimentally or theoretically, if such calculations would exist. To a few gigahertz, yeah, or 10 gigahertz or 50 gigahertz, yeah. That would be my dream candidate.
All right. Well, with this, thank you very much again, Piet. I'd like to point out the talk in 2 weeks is going to be by Ephraim Steinberg from the University of Toronto. He'll touch on quantum archaeology. And with this, well, thank you very much, Piet, for giving the talk. Thank you very much for the audience.
Thank you for staying with us.
Right.
Thanks for a great talk, Piet, and great to see you again.
Yeah, same here. Yeah. Okay.
See you.
Thanks.
Enjoy the rest of your Friday evening. Yeah.
Yeah, I will. Thank you. Bye.
Bye.
Goodbye.
All right. Thanks, Christian.